So we can start by saying that energy is the ability to do work. All right. Energy is the ability to do work. That is very, very true. And also, I want us to note that that energy is expended when work is done. All right? It is expended when work is done. And also, work and energy as the same units. They are both measured in joules. So we are saying that work and energy are both measured in joules. Joules. Okay. So sometimes you might see that we use energy as equal to force times distance. Don't be surprised, all right? Because when work is done, there is energy that is being expended in the process of work being done. So please take note of that. And also we have different forms of energy. We have different forms of energy, which I will give us some below. We have mechanical energy. We have chemical energy. We have solar energy. We have electrical energy. Heat or thermal energy. We have sound energy, and so on and so forth. All right, so these are some types or forms of energy that we have, and please note that these energies can be converted from one form to the other. So we are saying that these different forms of energy can be converted from one form to the other, and that is called the principle of conservation of energy. It's called the principle of what? Conservation of energy. It states that energy cannot be created nor destroyed, but can be converted from one form to the other. All right, so we can convert mechanical to electrical, we can convert light to sound, we can convert electrical to mechanical. All right, now these are made possible by some instruments or by some devices. I will give us some examples of some devices that can convert one form of energy to the other. I will start with a battery. A battery, number one, a battery. Now, a battery converts chemical energy to electrical energy. We also have a motor. A motor converts what? Mechanical energy to electrical energy. So, we have the light bulb. It converts electrical, which you got it, electrical to what? To its energy. All right. Also, we have a generator. Generator. This converts mechanical energy to electrical energy. All right. So these are some types of energy conversions. Okay. We have solar cells. Thank you. We have solar cells or solar panel. All right. Now, so solar cells convert heat energy, that's from the sun, to electrical energy. All right. So these are the some examples of some devices that convert the different forms of energy from one form to the other. So let's look at efficiency of a system. Now, as you all know, no machine is 100% efficient. The symbol we use for efficiency is written as this. This is the symbol we use for efficiency. This symbol is called eta. That's the symbol we use for efficiency. It's a Greek letter. Now, what is efficiency? Efficiency is the ratio of the useful output energy to the input energy. Is the ratio of the what? Useful output energy. So efficiency is the ratio of the useful output energy to the input energy. To the input energy. So this is the formula we use for efficiency as it relates to energy. And please note that efficiency has no units. It has no what? Units. Efficiency has no units, and it is stated as a percentage. So please note these very important points, that efficiency has no units and it is written as a percentage. Also, the reason why it has no units is because it is a ratio of the same quantity. As you can see right here, it's energy over energy. These two will cancel each other. So we say that efficiency has no units because it is a ratio of the same quantity. In this case, it's energy divided by what? Energy. It says a machine exerts a force of what? 250 newtons. So the force is 250 newtons. In lifting a mass through a height of 7 meters. So my distance is 7 meters. Now, please note that in this case, as you can see right here, work is being done. Okay, in this case, work is being done. So I can say that the work done in lifting the load is what? Is F times D, which is F is 250 times my 7 is, okay, 7 meters. That gives us what? That gives us 1750 joules. All right. Now, this is also equal to my output energy, because if you remember, I was saying that when work is done, guess what? There's energy being expended, which is given out. So the work done in lifting this load is the same as what? The energy that is what? Being expended or given out. So 1750 joules is also my output energy. Then it says 5 kg of energy is what? Supplied. That is my input energy. Is supplied. That's my input energy. Input energy of 5 kilojoules. Of 5 kilojoules. Now, to get your efficiency, if you don't mind, you can convert these to joules or you can convert these to kilojoules. But I want to convert these to joules, so it becomes 5,000 joules. 5,000 joules. So now I can find the efficiency, which is efficiency is equal to the useful output energy over the input energy. That will give us 1750 over 5,000. So therefore I can say that my efficiency of the system is equal to 0.35 is 0.35. We can put this in percentage. It can be equal to what? 35%. 35%. So here is the efficiency of this machine in lifting a force of 250 Newton through a height of what? 7 meters. So here is our final answer. So this energy is the energy that is due to motion. So it is the energy due to a body in motion. That is for kinetic what? Energy. It is the energy due to a body in what? In motion. Now the formula for it is we use KE is equal to half times the mass of the body times the speed of that body, or squared. So right here is the formula we use when we are asked to calculate the kinetic energy for an object. And please note that the M is the mass. M is the mass of the body. And the V is the speed of the body. So that is the formula we use to solve for kinetic energy. And please note that it is in joules. The next right here is potential energy. It is the energy of a body due to its position. It is the energy of a body due to its position. That is for potential energy. Let's imagine, for example, a ball or an object is raised to a distance of h. For example, we are raising an object. Look at this, please. Now, right here is a ball, and this ball is raised from this level to this level. All right? That's the ball. Now, this point where the ball was raised is called the reference point, or it's called the datum level. All right? Now, the work done in raising this ball from the reference point to the new position is equal to mg times what? The height, mg what? H. All right? It's equal to what? mgh. Now, this energy is stored as potential energy. So we say that PE is equal to mgh. And please note that m is still the mass of the body. The h is the height at which the object moved from the datum point to the new position. All right. Now our g is our acceleration due to gravity, which is equal to 9.81 meters per seconds squared. So right here are the equations we can use to calculate for kinetic energy and for potential energy. So right here I will show us the connection between potential energy and kinetic energy. Now, for the first case is when a mass is falling freely, we are told that that object's PE will reduce as it loses what? Height. In the same way, when the object is falling freely, the KE increases as its speed increases, ignoring what? Air friction. In this case, our equation becomes kinetic energy plus potential energy equal to a constant. This is when the frictional force is ignored. But when we do not ignore the frictional force, the equation will take a new dimension. Look at this. Now, in this case, when we do not ignore friction, or when friction is present, then there will be work done in overcoming resistance due to friction. In this case, the formula becomes initial energy equal to final energy plus work done in overcoming friction. We can also use what we call the work energy theory to show a connection between work and kinetic work energy. Now, this theorem, which is the work energy theorem, states that the work net, all right, it states that the work net or the network of a body is equal to the change of kinetic energy of the body. All right, so this is the work energy theory, or if you don't mind, principle of what work energy. It states that the network is equal to the change in kinetic work energy. From this, we can derive an equation for this statement. So I can say, therefore, that work net is equal to the change, look at this, the change in kinetic work energy. Now we can write this in equation. It becomes what? Equal to half m v final squared minus half m v initial all squared. In this case, the final speed is greater than the initial speed. But in some cases, when the object is retarding or is decelerating, the formula can change to this. It can become half mv initial or squared minus half mv final or squared. So we can use either of these equations depending on the final speed and the initial speed. If the final speed is greater than the initial speed, we use this one right here. But if the initial speed is greater than the final speed, then we use what? This equation right here. All right, so we can use either of these equations to solve questions that involve a change in kinetic energy. It reads, a lorry having a mass of 1.5 tons is traveling along a level road at 92 kilometers per hour. When the brakes are applied, the speed decreases to 28 kilometers per hour. Determine how much the kinetic energy of the lorry is reduced. Now, the first thing we do here is to write out the given data. Now the mass is given as 1.5 tons. So my mass is 1.5 tons. And in our previous classes, we learned how to convert tons to kilogram. And to convert tons to kilogram, we multiply by 1,000. So times 1,000. That gives us 1,500 kilogram. We are given the first speed or the initial speed. My V1 is 92 kilometers per hour, and our V2 is 28, or the V final is 28 kilometers per hour. So to convert these to meters per second, what we do here is that we multiply 92 by 1,000 and we divide by 3,600. All right, so this will give us that will give us 25.6 meters per second. The same thing for this, 28 times 1,000 divided by 3,600. That should give us 7.8 meters per second. Now we've gotten our speeds in the correct units. What we do next is to find the energy, which is the change in KE, and that will give us, now in this case, my initial speed is greater than my final speed, so I will use the formula half mv initial squared minus half mv final squared. So therefore we have half times the mass, which is 1,500, times the speed for V1 is 25.6 all squared minus half times the mass again, which is 1,500, times the final speed, which is 7.8 all squared, okay, good. Now when you put this in your calculator, you should get 491,520 minus, when you put this in your calculator, you should get 45630. So our final answer, or the change in kinetic energy, is 445,890 joules. 890 joules. So here is our final answer to this question. It says a ball bearing of mass 100 grams rolls down the top of a chute of length 400 meters, inclined at an angle of 30 degrees to the horizontal. Determine the decrease in potential energy of the ball bearing as it reaches the bottom of the chute. Now, the first thing I do right here is to try to visualize the situation. So I will draw a sketch of what the question is saying right here. Okay, look at this. So I draw a sketch of it. This is the horizontal, all right? This is my inclined plane, okay? Right here is the ball. The ball is rolling down the plane. Okay. Right here is the ball. As you can see, the ball is rolling down the plane. And also, it says that the length of the plane is 400 meters. That means that from this point to this point is 400 meters. And remember that the ball is coming down the plane. All right? Okay. Now, also, we are told that the plane is 30 degrees to the horizontal. So that means that this point is 30 degrees. Cool. Now, question. What is the potential energy? And we know that it is equal to, it is PE equal to mgh. And I know that my mass is given as 100 grams. So my mass is 100 grams. We can convert our grams to kilogram by dividing by 1,000. So that will give us 0.1 kilogram. And also, I know that my G is given as 9.81. So my G is 9.81 meters per second squared. Now, the question here now is to find the height. And I can find my height from this sketch. The height can be found from this point. Right here is where my height lies. Here is my height. To get the height, I will use my trig ratios. Okay? So I can use the sine ratio. So I can say that sine 30 is equal to the opposite, which is my h, over my hypotenuse, which is my 400 meters. So what next? I cross multiply. So my h is equal to 400 sine 30. So therefore, my h is equal to, when you put this in your calculator, you should get 200 meters. So now I have known my h, I have known my m and my g. So I can now solve for my potential energy, which becomes PE equal to the mass, which is 0.1, times my G, which is 9.81, times the height, which is 200. So therefore, my final answer should be 196.2. It's 196.2 joules.